Today we're going to start looking at our ratios in our proportional reasoning chapter. So in this little activity, I'd like you to look at these two pitchers of lemonade, and these are the recipes for making lemonade, and try to figure out which lemonade is more lemonade-y. So in the first pitcher, we have 2 lemonades for every 3 waters, whether they're cups or whatever we happen to, whatever, they're just equal amounts. So 2, let's call them cups, 2 cups of lemonade for every 3 cups of water. That is in the recipe calls, and you get a certain concentration of a lemonade, okay? Over here we have 3 lemonades and we have 4 waters. So which one has a stronger lemonade tasting? In other words, which one has more lemonade per a certain amount of water, or which one has less water for a certain amount of lemonade? So if we look at the very first picture, there's lots of different things we could do. What we could do is, well, we could say, well, what if I only have 1 lemonade? Let's cut the recipe in half. That means I only need 1.5 cups of water, right? Oh, and then we could do the same thing over here. Well, let's see how much water I would need if I only wanted 1 cup of lemonade. So this time I would go 4 divided by 3, which is about 1.3. So we can see that if I am using 1 lemonade, that this concentration, A pitcher, has more water, so that makes B more lemonade-y. Or I could have said, well, instead, let's just get 1 cup of water. So if I divide by 3, I get 1 cup of water. 2 divided by 3 is about 0.67. So we'll just say 0.6 for round, or 0.7 for rounding off. So we have about 0.7 cups of lemonade for 1 cup of water. If we divide by 4, right, I get 1 cup of water, and so since I've broken that into 4 equal groups, I need to break that into 4 equal groups, which is 0.75 cups of lemonade. So this one has more lemonade for water. You could have even said, well, let's find a number they can both become. Let's take our look at our water and say, hey, 3 and 4 can both become 12. I could have times by 4. I could have times by 4, right? Times by 3 over here, and multiplied by 3. Oh, I can see that I have more, whoops, it's supposed to be lemonade over here. I can see that I have more lemonade for 12 waters than I do here. So what I'm showing you here with ratios is that one ratio can be written with many different equivalent ratios. They're all equivalent ratios, right? You can even write a ratio with a decimal if you want, right? But in its simplest form, just like with fractions, 6 over 9, we could write a whole bunch of fractions equivalent with decimals, right? But the simplest form, fraction in lowest terms, just finds a greatest common factor, which I divide by 3, I divide by 3, and 2/3 is simplest form. Even though I could have divided by 4, right, and got decimals, I could have done any of that, but this is simplest form. Same thing with the ratio. Simplest form has no no decimals in it, and there are no GCF either. All right, so we're going to look at ratios today and talk about ratios. So another way to look at this is, okay, well, let's talk about what does a ratio mean. So here we have a prairie dog, and this prairie dog right here on the left is 3 units high and 1 unit wide, okay? And this prairie dog over here is 6 units high and 2 units wide. So we say this prairie dog is in proportion to the first one. It has been enlarged by a factor of 2 because we've doubled its height, but we've also doubled its width. So for example, if we take this prairie dog here, and I'm going to take this one, the original one, and let's say instead I didn't double the width, I only doubled the height. So if I only doubled the height, and now it's not working on me and I don't know why, let's just go and do and see if something happens or if I'm frozen. Let's try my mouse here. So there we go. If I only double the height, we can see it's not in proportion anymore. But if I only double the width, again, it's not in proportion. So whatever I do to one, I have to do to the other. What if I added 1 unit to the height and I added 1 unit to the width? It's still not in proportion. You can't just add. You have to, if you already have 3 and you have 1, you have to double what you have. You have to multiply to make a enlargement in the same proportion, or you have to divide, take half of it or a third of it, right, to make it a reduction in the same proportion. If you had a 3D dimension, you'd have to do the same to all 3 dimensions. So a ratio like length to width, right, as compared to, is in proportion if we multiply both sides by the same number or divide both sides by the same number. And it keeps it either as a recipe, it keeps it tasting the same, or as a picture, it keeps it in proportion. The picture looks the same. A good thing to note is a ratio compares 2 quantities measured in the same unit. For example, length and width are both distances, right? So centimeters as compared to centimeters, or inches as compared to inches, right? It could even be centimeters as compared to millimeters, because the centimeters can be converted to millimeters and we now have the same unit. So if one unit can become the other unit, then we can call that a ratio, right? Just like we could compare minutes to hours, because hours can be written as minutes. But we couldn't compare something like dollars and kilograms, right? Because dollars can't become kilograms and kilograms can't become dollars. So that comparing 2 units that are not equivalent or not the same is not a ratio. So when we have ratios, what we can do with ratios is we can write them in lowest terms. So just like we would write a fraction in lowest terms, we would find a greatest common factor that goes into both. So I first see I can divide by 100. Oh, now I can divide by 3. And we write that this ratio is 15 as compared to 1. Or we can say short, it's a 15 to 1 ratio. Here we have minutes and hours. And so I have different units. If the units aren't the same, I have to make them the same so that I can eliminate them, right? A ratio is considered unitless because the units can cancel out. So then I can put any unit I want in, and it tells me, okay, I've reduced something by 15 or I've enlarged something by 15 times greater, right? Doesn't really matter the unit, you just keep the same unit. So here they're different. So I have to change 3 hours into minutes. Well, there's 60 minutes in an hour, so we have 180 minutes. Now that my units are the same, I can leave them out. Now I can divide both sides by 10, and then 3 goes into both, so I get a 1 to 6 ratio. 1 minute for every 6 minutes. Again, here we should know that centimeters, centi meaning 100, there's 100 centimeters in a meter, so we can change our 9 meters into 900 centimeters. And then our centimeters cancel out. Now we can divide both sides by 6, I believe. Let's pull up the trusty calculator, and yes, 150 as compared to 1. Another common unit is good to know. Kilo means 1,000. There are 1,000 grams in 1 kilogram. So 2 kilograms is 2,000 grams. So we can convert to make them the same. Now we can cancel out the units. Now we can divide by 100, and that's as much as I can do. So we get 20 as compared to 3. You know, I could divide both sides by 3 and get a decimal there, but that would not be in lowest terms or simplest form. We could also find a missing part of a ratio, given that we know 2 ratios are equivalent. So if I know 1 to 3 is equal to something to 6, sometimes writing it vertically helps out a lot. So if we write it vertically, we can see, oh, look at this ratio. If I'm going in this direction, I am multiplying by 2 because 3 times 2 is 6. If I was going in the reverse direction, I'd be dividing by 2 because 6 divided by 2 is 3. If you ever do not know what that number is, the 2, because it's not easy to see, you can always figure out that number by taking the larger number divided by the smaller number. Since I know the 1, I am moving in this direction, so I am multiplying by 2. So I know that is 2 to 6. Let's try another one. What to 3 is equal to 10 to 15? Oh, I am multiplying by 5 this way, or I'm dividing by 5 this way. I can see I'm going this direction, so I want to divide by 5. So the answer is going to be 2. 2 to 3 is equivalent to 10 to 15. So we can use our equivalent ratios to fill in missing parts of a ratio. This one is 6 to 5 is equivalent to 51 to something. Here's an example where I'm like, okay, well, how am I getting from 6 to 51? I'm not sure. I don't have that one memorized. So if I take 51 divided by 6 on my calculator, I can go, oh, it's 8.5. I now know since I'm getting bigger, I would be multiplying. If I was going smaller, I would divide. I now know that I'm multiplying by 8.5. So whatever I do to one side, I have to do to the other. And I get 42.5 is that missing piece. You can get a decimal, that's fine. It's just not in lowest terms, right? 6 to 5 is my simplest form. Sometimes I can give you 3 ratios, right? 3 to something is equal to, and again, I'm missing pieces in both of those ratios. So if you write them out and you line them up vertically, it makes it a lot easier to see, right? Blank to 45 to 20. So I've lined them all up, and now I can see that I know this one number and this number, they line up vertically. So this is what tells me, oh, if I'm going this direction, I multiply by 5. So 3 times 5 is 15. Oh, if I'm going this direction, I divide by 5. Oh, so 45 divided by 5 is 9. You can find those missing pieces by lining them up. So I know 3 to 9 to 4 is an equivalent ratio to 15 to 45 to 20. So that is finding equivalent ratios. You can write ratios given a situation. So if I wanted to write a ratio of red marbles to black marbles, I would just count up the number of black marbles, and I would count up the number of red marbles, and I'd count up the number of black marbles. And marbles are common units, so I don't have to write the word marbles twice. It is a 4 to 16 ratio, which could then be reduced as a 1 to 4. So this tells me the proportion of red as compared to black is 1 to 4. So if I wanted to add more marbles and keep them in the same proportion of red to black, I could add 1 red marble and 4 black, or I could add 2 red marbles and 8 black, etc. I could write it as a 3-term ratio. So I would have 6 blue as compared to 4 red as compared to 10 black. You can compare 3 things in a ratio. Keep them in the same order that you read them. That's super important. Otherwise, we don't know which number goes with which. So the words are really important to keep the order. And then you could reduce it by dividing each number by 2. I would get 3 to 2 to 5. That would be my ratio. Red to total number would be, well, there are 4 as compared to 20 marbles. I even told you so you don't have to count. Now, whenever the second number is a total, we call this a part to total ratio. A part to total ratio could also be written as a fraction. Red as compared to black in the first question, the 4 represents part of the group, the 16 represents part of the group. You cannot write this as a fraction. You could not write 4 over 16. You could not write 1 over 4. It wouldn't make sense because in a fraction, the bottom number means out of the total, right? So if you wanted to make this one into a fraction, right, you would have to combine the terms, right? For example, let's take a look at this last one to show you what I mean. Red represents 4. Not red represents the others, which is 16. So therefore, 4 out of, if I added them together, I would have the total, right? 4 out of the 20 are red, just like we got in the last question. So you can see how those ratios are equivalent, right? Because it's a part to part, and I've changed it to a part to whole ratio. All right, let's try another question. A fishery department captured and tagged 300 salmon. So they go out and they catch 300 salmon. They put a tag on their fin so that later if they catch that salmon again, they can keep track and they can know that that salmon is still in the population of salmon. So this is a good way, and this is what's used at the fishery department and many different places to track population of different species. So what's going to happen, so we know we've put 300 salmon back into the ocean and they've all been tagged. A month later, they go and capture 40 salmon. Of those 40 salmon, 5 of them have tags. So the proportion of salmon that have tags as compared to 40 total salmon. Oops. So we know there are 5 out of the 40 that are tagged. So what we can do with this is we can predict by knowing that, okay, well, if 5 of them are tagged and we have 300 tagged salmon out there, then how many salmon do we estimate are actually in this location? Well, 300 salmon represent the tagged. That's how many we tagged, right? 5 salmon are tagged for every 40 we catch. So if there's 300 tagged out there, well, we could create an equivalent fraction. Oh, I'm just multiplying by 60. So I'm going to create an equivalent fraction and multiply by 60. Oh, my estimate is there's 2,400 salmon in the population based on the number of tagged salmon I caught out of the total number of salmon I caught. So we used ratios to predict the population. Some of us might have made oobleck before, maybe in elementary school, where you mix your cornstarch with your water. And when you make it in a certain proportion, following the recipe, when it's all mixed together, if you go to hit the oobleck really hard, it's in a solid state, and you can't. It's like knocking on a door. It's solid. But if you rest your hand softly in it, it turns into a liquid and turns into slime. So this oobleck recipe calls for 2 cups of water and 1 cup of cornstarch. So 2 cups of water for every 1 cup of cornstarch. I'll just write starch so I don't write so many words. Okay. So this is where it gets a little tricky because I want to now make 24 cups of oobleck. Well, the recipe is a 2-to-1. It's a part to part, right? What fraction of the oobleck is water? Well, 2 parts is water and 1 part starch, so we have 2 parts water for 3 parts oobleck, right? I think I'm saying that right. 2 plus 1 gave me the 3. So sometimes in your ratio, you have to add them together to find the total, right? And so now if I want to make 24 cups of oobleck, I need to now know, oh, let's make an equivalent ratio. Oh, I'm multiplying by 3, so I need to multiply by 3. Oh, I need 6 cups of water if I want to make 24 cups of oobleck. So we have to be careful that we don't just use the 1 and 2, and sometimes we need to add them to get the total. Here's another example like that, our last one today. I have an 850-gram cereal box. It is labeled 3 parts rice, 6 parts wheat, and 8 parts oat. Okay, so that is the proportion of the different grains in my cereal. If this box comes in an 850-gram total amount, then how many grams of wheat are in this box? Or I could ask how many grams of rice or how many grams of oats. I don't know how many grams of each of those are, but I know if I added all the grams together, I would get 850, right? Or in other words, if I added all the parts together, I would get 17 parts. So I can use that idea again to say, okay, well, we have we want to just look at the wheat. So 6 parts are wheat out of a total of, and we could write it as a fraction or a ratio, it doesn't really matter, out of a total of 17 parts total, right? The rice, the wheat, plus the oats is this number. So if the total cereal is 850 grams, then how many parts or how many grams are wheat, right? Because if that is grams, this will be grams as well because they are the same unit, right? So we need to figure that out. So how am I getting from 17 to 850? I don't know. I don't have that one memorized. So I type into my calculator 850 divided by 17. Oh, it's 50. So I know since it's getting bigger, I'm multiplying by 50. So whatever I do to one side, I do to the other to keep it in proportion. So I multiply by 50, and I now know there are 300 grams of wheat. All right, so again, those ones are tricky because you had to come up with that 17 by combining all the parts to make the total.